let's do a little quick vocab review before we get into it. When this problem says least possible degree of the polynomial, that means the exponent power at the very front of the polynomial, the biggest exponent that it has. So what we're looking for is the exponent power of the polynomial that made the data in this table right here. Now, I don't know exactly what that shape looks like. I've got an idea. I could probably make a plot. But before we get into plotting that data, I want you to come over here on the right side where I've listed out just some functions that I think are kind of cute and related to what we're doing. So we have a quadratic function. Okay, that's my first one. This quadratic function is a second power. That means it has an exponent of 2 on it. And if you notice, it has one turning point, exactly one turning point right here. We usually call that a vertex. Okay, great. So our cubic function, that's a third power, that has 2 turning points, right here and right here. And then the quartic power, that's a fourth power function, that has 3 turning points. Now, not every single quartic and cubic function looks like these, but often they do, unless it's a weird situation. So hopefully you notice the pattern at this point. If you have 1 turning point, you're quadratic. If you have 2 turning points, you're cubic, right? 3 turning points makes you fourth power. So the power is always 1 higher than the number of turning points. Now, there's exceptions to this, but by and large, it's a pretty good rule, especially when we're talking about the least possible degree. Okay, so let's draw a graph and pretend those are nice straight lines that I just drew. So here's my graph, and I'm going to put those dots on it. So at x equals 0, my output is -7. At x equals 1, my output is -22. That's like down here. I know the scale is not right on the graph, but I get to do stuff like that because I'm not an art teacher. At x equals 2, my y value is back to -7. At x equals 3, my y value is up to -2, or to +2, excuse me. At x equals 4, we're back down to -7. Really like that -7. At x equals 5, we're at -22, so way down here. At x equals 6, we're back up to -7. At x equals 7, oh gosh, 98. I don't think that's going to work with my graph, but we'll just pretend. You know, I can just say not to scale, and that excuses all my mistakes. X equals 8, well, that's huge. That's like 400, so I'm going to draw that slightly higher than 98. Okay, now let's make an attempt at drawing our graph. Over it goes. And you might argue with me about some of the directions that I chose. For example, how do I know that it doesn't do this between those last 2 points? I don't, but let's make this as least complicated as possible as a way of getting to the least possible degree. If you make your polynomial more complicated, of course you would have a higher exponent to explain that, but we're looking for the least complicated one. So if you count the number of turning points, I've got 1, 2, 3 turning points in this function. That means it must be a quartic function. The minimum it is a quartic function. Of course, maybe it's 5th power or 6th power or 7th, who knows? But it's at least a 4th power because I found 3 turning points in the graph.